Okay, so I want to talk about Assouad dimension, and in particular, an Assouad dimension analog of the distance set problem, or the Falconer distance set problem, as it's sometimes known. And I'm going to introduce these things, just in case there's anyone in the room who hasn't come across it before. And I'll state some results and hopefully give some proof towards the end. So let me start by recalling the problem. This is the distance set problem, which I don't think has been mentioned in any talks so far this week, so it's my pleasure to introduce it for the first time. So this is a problem going back to Falconer in '85, which has attracted a lot of attention and a lot of interest in the literature and the community and ever since. And not just the problem itself, but also many variants of the problem which have a similar flavor. I'm not going to talk about those today. So the basic problem is I have a set X in RD. Throughout the whole talk, X is Borel. And it's even going to be compact later on. You lose nothing if you think X is compact the whole way. And I define, given this set X, I define a set D of X, which is the distance set associated to X, which is simply the set of all distances realized by pairs of points in the set X. So there's the definition. This is the distance set associated with my Borel set X. And this is a subset of the real line. So even though X lives in RD, the distance set lives in the line. And the basic problem, there are many ways to formulate the problem precisely, but I want to formulate it slightly imprecisely first. So the problem is it true that X big implies D of X big? This is not a statement, this is a question. So it seems intuitively reasonable that if I have a set which itself is very, very large in whatever sense you wish, then probably it realizes a lot of distances. It seems like a reasonable thing to try to verify in various settings. So let me give you a precise version of the problem stated as a conjecture. So I'm now going to quantify big in terms of dimension. So is it true? So this is a conjecture. It's open as long as D is bigger than 2. So the conjecture is that if the Hausdorff dimension of X is big, what does big mean? Big means half of the ambient spatial dimension. So if the Hausdorff dimension is at least D over 2, then this should imply that the distance set is big. What does big mean? Well, as big as it could possibly be, which means the Hausdorff dimension is 1. Well, this is an open problem, open conjecture, and for all B at least 2. So we know that as I said before, well, lots of interest in this question over many years. Contributions from many people, some of whom are in the room. So let me just tell you, I certainly can't give an extensive review of everything that's been done on this problem because it's an extremely large literature. But let me just tell you a couple of highlights. So, for example, we know that if the Hausdorff dimension of X and the packing dimension of X are the same, then it's true. It's like this. So if I make the additional assumption that X has homogeneity prescribed by equality of Hausdorff and packing dimension, then this conjecture holds. So this is a recent result of Schmerken and Wang. I'm going to give years for some papers, but when they're extremely recent, I don't remember the year. So this just means it's an extremely recent paper in the last year or 2. So this is Schmerken and Wang. We also have some partial progress without making assumptions like this, where partial progress can be, you can imagine lots of different ways to get partial progress towards this conjecture. But for example, I might want to try that if the Hausdorff dimension is at least some number which is bigger than d over 2, then that guarantees that the Hausdorff dimension of the distance set is full. And there's lots of work in this direction. So I think the state of the art is that if the Hausdorff dimension of X is at least d over 2. You have to check archive every day if you want to really say the state of the art in this question. But I don't guarantee that this is actually the state of the art at this very minute. But we do know that if the dimension is bigger than d over 2 plus a quarter, then that's enough to ensure that the Hausdorff dimension of the distance set is 1. So this is due to Wren and Wang, also very recent. So Falconer himself in 1985 put the number 1/2 here. This 1/2 was reduced to 1/3 by Erdogan and Wolf. And then the 1/4 is just recently due to these authors. So these are probably these are two of the strongest results in this problem at the moment. But there are many very impressive contributions that have been made to this problem. But I apologize for not being able to mention them all. Right. Okay. So people who've seen me give talks before probably know that I like to embrace the full catalog of notions of dimension which we have available to us. And so when I first saw this problem, I thought, well, why are we always so excited about the Hausdorff dimension? Right? The life doesn't stop just with the Hausdorff dimension. There are lots of other perfectly reasonable ways to define fractal dimension. There are already even some on the board, for example, the packing dimension. And so what if you try to formulate this conjecture for some of these other notions? What happens? And so I'm going to tell you about the Assouad dimension version of the problem. So this is where I replace Hausdorff dimension with Assouad dimension. And so in order to state the result, I'm going to tell you a little bit about Assouad dimension first. This is a good opportunity, I think. The chair pronounced Assouad as Assoud. I say Assouad. I've written a book on the topic. That doesn't make me an expert necessarily. But Assouad was a Frenchman, and so we have lots of Frenchmen in the room, French people in the room. So perhaps this is the chance to finally settle it once and for all. So how does one pronounce Assouad? Assouad. Okay, perfect. Right, from now on, it's settled, and I have lots of reliable witnesses, some unreliable as well. Okay, so Assouad dimension. So see the course last week by Antti Kanmäki. So this is like a prerequisite to this talk somehow. Antti gave I wasn't there, but I heard that he gave a wonderful introduction to Assouad dimension and actually focused on things which I'm going to use crucially in this talk. So let me give you the definition of the Assouad dimension. So the Assouad dimension, dim A of X. Okay, X is now compact, just to avoid any technical issues that I don't want to encounter. So the Assouad dimension is the maximum of the Hausdorff dimension of E, such that E is weak tangent to X. I'll tell you what a weak tangent is in a second. And yes, this isn't the definition of Assouad dimension, actually. This is a theorem. But you'll know through your experiences in mathematics that sometimes if a lemma is really good, it can become a theorem. And this is like somehow the ambition that a lemma has. But if a theorem is really good, like really, really good, it can become a definition. And so actually this theorem is so good that I want to use it now as the definition of Assouad dimension. So this definition is actually a theorem due to Kanmäki, Ojala, and Rossi from 2018. So it's Clarence gave you the definition, the original proper definition of Assouad dimension, and it's a theorem, non-trivial theorem, due to Kanmäki, Ojala, and Rossi, that the Assouad dimension, in fact, can be defined like this. So what's a weak tangent? So E is weak tangent to X if there exists some sequence Cn, probably want Cn to blow up, and a corresponding sequence of translations such that Cn, so X scaled by Cn translated by Tn intersect the unit ball converges to E. How does it converge to E in the Hausdorff metric? So it's very simple. It's you take little blow-ups of your set, you take limits of the sequence of blow-ups. If you get a limit in the Hausdorff metric, that's a weak tangent, very closely related to the familiar notion of the tangent of a curve, for example. So here's a picture. Here's X. I take a little part of X, I blow it up to the unit ball. I take another little part of X, blow it up to the unit ball. I take another, perhaps even smaller part of X, I blow it up to the unit ball. This gives me a sequence, and this sequence limits to the tangent E. So Assouad dimension is a local notion, and this is picking up structure local to sort of make sense on an intuitive level that this characterization should be allowed. Okay, so I want to say things about the Assouad dimension. And maybe it's useful to recall, Richie already said this yesterday, but the Hausdorff distance, yeah. The Hausdorff dimension is always a lower bound for the Assouad dimension. That's perhaps useful to keep in mind. Okay, so now I want to work towards talking about the Assouad dimension analog of this distance problem. But before I do that, I'm going to talk about projections, because I'm going to prove the distance set result in the context of nonlinear projections. And the only way to handle nonlinear projections is to linearize. And so I'm first going to talk about linear projections. So this is like a third section. So we had distance sets, Assouad dimension. This is the third one, which is projections. There's only one more section after this. So let me just recall a very influential theorem due to Marstrand from 1954. So this says that Marstrand, let me state the general RD version, which is due to Marstrand and Mattila. Mattila is 70, something like that. So X is my Borel subset of RD. Marstrand's projection theorem says that the Hausdorff dimension of the projection of X onto a subspace V, I'll quantify these things properly in a second, is the maximum of K and the Hausdorff dimension of X for almost all V in V dk. So, oh yeah, then. Yeah, thank you. It's definitely false if you put maximum. So what this is saying is it takes some set, and then I want to try and understand this set by projecting onto subspaces of dimension K. Then Marstrand-Mattila projection theorem says that the Hausdorff dimension should be as large as possible, almost surely. That's what this result says. And despite the fact I just misstated it, this is probably my favorite theorem. I quite often get asked what my favorite theorem is. I think that's this. So I want to use linear projection. So this is linear because I'm projecting onto linear subspaces. I want to use linear projections to study this Assouad dimension problem. So I should probably first try to understand Marstrand's projection theorem in the context of Assouad dimension. So this is something that I worked on some years ago. So let's see. So this is something I proved together with Thomas Orphan in 2017. So this is that the Assouad dimension of the projection of X onto a subspace V is at least the minimum, thanks Kenneth, of 1 and the Assouad dimension of X for almost all V and D to 1. So I'm now setting D equal to 2 and K equal to 1. So that's why this K became a 1. And I'm now talking about one-dimensional subspaces of R2. So it looks a bit like Marstrand's theorem, but it's not the same because we only have at least instead of equal. But in fact, we also proved in this paper that you can't do any better than this. So in particular, there is no Marstrand theorem for Assouad dimension in the sense that the Assouad dimension of the projection does not need to take on a common value almost surely. And then that's quite horrifying in some ways, noting that the Marstrand type theorems were established in the 90s by Falconer and Yarvan-Paz and other people for box and packing dimensions. So they do satisfy a Marstrand theorem. So Assouad dimension does not, but we still do at least have this lower bound almost surely. And if you want to know how bad the behavior of this number as a function of V can be, then the answer is it can be really bad. And this is something that I studied in depth with Antti I think it was published in 2020. So here we just construct examples where this has unbelievably bad behavior. So for example, it's even true that you can construct a set X in the plane such that this function takes a different value for every V. Think about that for a second. That's really far from a Marstrand type phenomenon. Okay, so then okay, what about higher dimensions? So this was 2017. We proved this lower bound using some additive combinatoric methods. It was not completely straightforward, I would say. But then Kanmaki, Ojala, Rossi came along in 2018, notice it's 1 year later. And actually with this characterization of Assouad dimension, it's extremely easy to prove this theorem. And in fact, I can then extend it to higher dimensions in an extremely straightforward way. So this is now in 2018 using the definition over there. And it's the thing you expect. So the Assouad dimension of the projection is at least the minimum of K and Assouad dimension of X, almost surely. So how do you prove this? Well, you take a tangent which witnesses the Assouad dimension. You then observe that the projection of a tangent is a tangent of a projection, and then you apply Marstrand's theorem. It's one line if you write small. But then, so this of course generalizes the theorem up there, and also by using the same approach, one can get. And I'm not going to go into this too much in this talk, but there's a lot of interest in estimating the size of the exceptional set in these types of theorems. And this approach, which I just gave you for proving this, allows you to take any result on the exceptional set for Marstrand's theorem and state it similarly for the same bounds will work for the Hausdorff dimension of the exceptional set in the projection theorem for Assouad dimension. But Thomas did much better than that. When was this? Maybe 2020, certainly after 2018. So in the plane, so this is again D equals 2. In fact, the Assouad dimension of PVX is at least, should have had some shorthand for this. I'm writing it rather a lot. So this holds not just almost surely, but for all V apart from a set curly E with Hausdorff dimension 0. Right, so this is like you can't prove this by using the known exceptional set results for Hausdorff dimension because it's not true for Hausdorff dimension. So this is going deeper and using something specific about Assouad dimension. So in fact, it's extremely generic that the Assouad dimension of a projection is at least this number. Because the collection of V for which this fails has Hausdorff dimension 0. The old one, I think. Yeah. I don't think I understand the question. Oh, sorry. Good. Yeah. No, I don't think. I think the exceptional set can be full packing dimension actually. So that's one way of answering the question. With the Hausdorff dimension 0. Sorry, I didn't even write. Virtually Hausdorff dimension 0 for the exceptional set. I don't know of any way to do better than that. And by better could mean something like replacing Hausdorff dimension with some bigger notion of dimension. So anyway, I'm not just telling you this because it's a nice result, but I'm going to use it rather crucially. Okay. Any other questions? So we understand the orthogonal projections from a point of view of Assouad dimension pretty well. At least in the plane. So okay, now this is the final section. I'm going to state the theorem, which I want to talk about. So this is something I proved during the pandemic. I remember that very distinctly because somehow that was a very clear period of time in my mind. But it was published in 2023. So this answers the problem. It solves the distance set problem for Assouad dimension in the plane. So the solution looks something like this. The Assouad dimension of the distance set of X is a compact subset of the plane now, is at least the minimum of 1 and the Assouad dimension of X. So this answers the question because if the Assouad dimension has to be bigger than half the ambient spatial dimension, well, the ambient spatial dimension is 2. So if the Assouad dimension of X is bigger than 2 divided by 2, which is 1, then this minimum is 1, and the Assouad dimension is full, the distance set is full Assouad dimension. And this is also sharp, so you can't do any better than this, even for subcritical X. So if X is such that the Assouad dimension is less than 1, then this bound is the best you can do. Okay, so I'm going to prove this theorem. And I'm going to prove it using this definition of Assouad dimension. I'm going to use Orponen's projection theorem as a black box. And I'm going to use a nonlinear projection theorem, which I proved in this paper as a black box. I'll tell you what it is when I come to it. But otherwise, I can give you the complete proof. Maybe I'll start a new board. Okay. So here is X, lives in the plane. I'm going to take a weak tangent of X, which I'm going to call E, as usual, which witnesses the Assouad dimension of X. So the Hausdorff dimension of E is the same as the Assouad dimension of X. Let me write that down. And I can do this because of tan macchioggia Rossi. Then I'm going to take another weak tangent, this time of E. And it really is necessary, at least as far as I understand, to do this double layering tangent. I'm going to take a tangent of E, which I'm going to call E prime, and I'm going to even be more specific. So all these sets are compact. So if I take a sequence of blow-ups of the set E, which are blowing up at a particular point at a particular scale, then because this set is compact, the points at which I'm blowing up have to have a limit somewhere. And I'm going to call that limit point Z. So that point is there. So this is what I call the focal point of the tangent, E prime. So I take, so E is just any old weak tangent of X which witnesses the Assouad dimension. Then E prime is a weak tangent of E, which also witnesses the Assouad dimension. And has focal point Z. So the E can be found near Z, basically. Little copies of E, which limit to E prime, can be found near Z. That's what the focal point. And I'm using compactness there. The Assouad dimension of E cannot be larger, actually. The Assouad dimension of E must be the same, because just because of the relationship between Hausdorff and Assouad dimension. If the Assouad dimension was larger, then I could then take a tangent of that set, and then, oh, I mean, I've already done it, right? So E prime is a tangent of a tangent. A tangent of a tangent is a tangent, right? And so that would be a contradiction. Good question. Right, what am I going to do with this setup? I'm now going to let curly E, so curly E was what I used for the exceptional set in Orpinen's projection theorem, and I'm going to also let it be the exceptional set for Orpinen's projection theorem again. But it's going to be the exceptional set for Orpinen's projection theorem applied to the set E prime. So this is Orpinen's exceptional set for E prime. Now I'm going to use two different types of nonlinear projection. One of them is going to be radial projection, and the other one is going to be the pin distance map. So maybe these objects are familiar to you. If not, I'm going to define them right now. So for radial projections, I'm going to write as so. Radial projection, I'm going to denote by pi z. So for a radial projection, I think it's better to draw a picture than to give you a proper definition. So radial projection fixes a pin Z, draws a unit circle around Z, and then projects everything in the plane apart from the point Z onto the boundary of the circle at right angles. So this is some point Y. This point here is pi Z Y. This is projecting along lines but onto a target set, which is a circle. So this is called a radial projection of projecting along radii. And I'm also going to use the pin distance map, which I'm going to write as D, capital DZ. So this just sends points to distances. Let me draw a picture. So the pin distance map DZ just sends points Y to the distance between X and Y. Right. This is also a nonlinear projection for the following reason. So here is Z. So this time, what happens I sort of pretend that this is the real line by translating z, then this time a point y will project non-linearly like this number, distance between z and y if I abuse notation by pretending that z is at the origin. Now, so these are two types of nonlinear projections. So I'm going to break the proof of this theorem up into two cases. I'm going to use these nonlinear projections and the other ingredients that I've mentioned in both. Okay, so case one. So look up at the picture here, this hierarchy of tangents. The pin for the radial projection and the pin distance map is going to be z. So that's the focal point of the tangent E prime. And the two cases I'm going to consider are, one, if the Hausdorff dimension of the radial projection with pin z of E is 0 or not. I'm going to do the greater than 0 case first. Right, so that's the number. It's either 0 or not 0. That's the two cases. So the first case, suppose the Hausdorff dimension of this radial projection is positive. Well, think about what radial projections mean. So the radial projections are like identifying directions determined from Z. So directions you can determine in a set from looking from the point Z. And this is in one-to-one correspondence with one-dimensional subspaces of the planes. And so if the Hausdorff dimension of this set is bigger than E, then I must be able to find a direction which is different, well, which is not an exceptional direction for Orpin's projection theorem. Right, so this implies that there exists another point, X in E, such that the subspace determined by the direction of X from Z, so that's the span of Z minus X, is not in the exceptional set. Why? Because the exceptional set has dimension 0 by Orpin's theorem. So if this direction set has positive dimension, then I must be able to find a direction which is not in the exceptional set. So now, what do I want to estimate? So I want to found the Assouad dimension of the distance set of X from below. Right, that's what the theorem tells me I should do. Now, how did I prove the projection theorem for Assouad dimension in higher dimensions using Can, Macchioglia, Rossi? Well, I said that it's extremely easy because you just take a projection of a tangent as a tangent of a projection. Well, the distance set is not so different from a projection, and you can do a little bit of work along the same lines to establish that the Assouad dimension of the distance set of X must be bounded below by the Assouad dimension of the distance set of E. Because E is a tangent to X. Right, let's think about the distance set of E now. Look up at this picture. And I'll add the point X to this picture. So here is X. And X was the point where I have this span, this one-dimensional subspace not being an exception to Orpin's theorem. Now, E prime appears as a tangent to E near Z. So what happens if I consider not the distance set of E, but just the distances determined from X, right? Well, distances determined from X to points very near Z looks extremely like an orthogonal projection of E prime. Right, that's the nonlinear projection theorem that I mean, there's work to do there. This is the technical part, but it's heuristically hopefully clear. That if I look at distances, if I'm looking at the distance set of E, I'm only going to look at distances determined from the point X. And I'm only going to look at distances determined from the point X, which are extremely close to Z. Well, if I zoom in on that picture, what I get is something like this. So here is X, same X is over there. Here is Z. If I zoom in close to Z, I get something which looks like E prime. And so if I blow this up, I get something which looks like E prime. And the pinned distance map looks very much like orthogonal projection onto the span of X minus Z. Right? Because if I like the pinned distance map moves points along these circles, but if I look very, very close to Z, those circles just become lines, and the distances are realized here as an orthogonal projection of E prime onto the span of X and Y. So modulo the details, this is, by this nonlinear projection theorem, this is at least the Assouad dimension of the projection onto the span of X minus Y of what set? What set should I write here? E prime, great. I always, when I'm in the audience, I hate it when the speaker does that. So I'm not in the audience, so this is my opportunity to do it. This is Z, sorry, yes. Yes, there is no Y. But now what's this? Well, the span of X minus Z is not an exceptional direction in Orpinen's theorem. So this is at least the minimum of 1 and the Assouad dimension of E prime, which is the Assouad dimension of X. So we're done in that case. Right, what about case 2? So case 2, the Hausdorff dimension of the radial projection phi at Z, that's the focal point up there, of E better be 0. Right, so now perhaps all of the directions witnessed from Z are exceptions to Orpinen's theorem. Right, that's the situation I'm in. So now I have to make the gain by using the fact that the Hausdorff dimension of this radial projection is extremely small. So what I'm going to do is rebuild the set E from the radial projection and the pin distance map. So here, let me write something and then explain what it means. So the set E, that's the middle set in this hierarchy, must be contained in, well, I'm looking at the set from Z, and what I know is I know the directions which are determined, and I know all of the distances which are determined. So that determines all the points, and plus many more, but it certainly determines all the points. So E will be contained in the radial projection of itself with the pin Z. Okay, it's not so I write it like this. This is what I'll explain what this is in a second, but it's like a radial product or something with the distance, the pin distance set. Right. So what is this set formally? Maybe I should write it down. So I want Z plus mu times Z minus X divided by the modulus of Z minus X, where X is in, so X is determining a direction, so X is in here, and mu is determining a distance, so U is in here. I don't think this definition helps, but I think the heuristic behind it is much easier to understand. So what this is saying is that if I give you a pin Z, and I tell you from that point, all the directions which are determined by E, and all the distances which are determined by E, then this information must be enough to recover E, and many more things. And this will be a much bigger set than the formal definition of this. So what this is saying is, what this means is here is Z, here here is x, which lies on this circle, is z plus f1. And so this point x determines a direction. Then the distance u determines a point which is at distance u from z in direction determined by x. And of course, all points can be expressed in this way, so therefore E is contained in this set, right? Okay, so products are reasonably well understood objects in fractal geometry. And if I want to bound the dimensions of a set in terms of dimensions of a product, then there's all sorts of nice ways of doing this. Okay, usually we work with Cartesian products, but this is close enough to a Cartesian product that with a very simple argument, you can establish the usual type of product phenomena. And so what this allows me to do is deduce that the Hausdorff dimension of E, well, that's certainly less than the Hausdorff dimension of this product. How do you bound the Hausdorff dimension of a product from above? You unfortunately, it's not equal to the sum of the Hausdorff dimensions, but you can bound it above by the Hausdorff dimension of one plus the upper box dimension of the other. So I'm going to do that. So this is bounded above by the Hausdorff dimension by ZE plus the hacking dimension, upper box dimension, whichever is your favorite, of DZE. Right, that's just the usual product type phenomenon which we give in fractal geometry undergraduate courses. And now I'm almost done. So continue over here, resisting the temptation to try to complete the rest of the proof in that little space at the bottom of the board. Done it too many times before in the past, and I'm learning. So look at that bottom line. Well, I can bound the Hausdorff, well, the Hausdorff dimension of E is the Assouad dimension of X, right? Remember? So the Assouad dimension of X is bounded above by this. This is bounded above by the sum of these two numbers. Well, thank goodness, this one is 0. Right, the whole point of this case is that the radial projection with pin Z has Hausdorff dimension 0. So this number is 0. The packing dimension of the image of E under the pinned distance map Z, well, this is certainly bounded above by the Assouad dimension of the image of E under the pinned distance map at Z. But that's by inclusion bounded above by the Assouad dimension of the distance set of E. And then because distance sets are very closely related to nonlinear projections, it can be linearized. And E with a tangent to X, this gives a lower bound for the Assouad dimension of the distance set of X, and I'm done. Because all I wanted to prove that the Hausdorff dimension, the Assouad dimension of the distance set is bounded below by the minimum of 1 and the Assouad dimension of X. So this is better. So in this case, it's the Assouad dimension of X. So that's the proof finished. Right, so Mark said that if I gave a completely incomprehensible talk, I could talk till 11:50. So maybe I can stop now with the hope that I've given a comprehensible talk and therefore there'll be questions. So I'll stop there.